This is yet another Ryobi OnePlus battery charger gets video. This particular one is a P131. This is their charger that runs off of a 12 volts, intended for in-vehicle battery charging applications. And other than that, it looks to be fairly typical for one of these things. Switching power supply transformer, which in this case is designed for a 12 volt input, and I'll get to how that appears to be connected in a bit. Unlike the others though, this employs a separate switch mode supply driver chip, in this case a UC3843B, and a switching device. It doesn't employ the all-in-one type switch mode controller with built-in switching device that the P117 and P118 had. But anyways, that's probably just because of this is, I don't know if those kinds of devices are fairly common for 12 volt input applications like this one is. But anyways, then there's a rectifier that's probably going to be a Schottky of some sort. Actually, it would almost certainly have to be a Schottky, because that in this application would have substantially lower loss than a regular high-speed rectifier, or high-speed silicon type rectifier. One current sense resistor, more current sense or current limiting resistors, and still more current limiting resistors. The battery contacts, which unlike the other two controllers that have done gets videos of, or chargers that have done gets videos of, these just have 3 separate contacts that mount the holes in the printed circuit board. There isn't a plastic frame supporting them all. And also, unlike the others, this one has a the secondary temperature switch or thermistor, might be a temperature switch, I haven't checked, contact is mounted to a little protrusion on the top of the case. It isn't part of the plastic frame holding the other 3 main contacts. And also, this one happens to have this unused contact marked T, which is, I guess, just something for some future electrical purpose, for some future expansion of the Ryobi OnePlus system, which is good to see as far as actually designing stuff for future upgrades and whatnot, because that's something that's never done nowadays, because the idea is that everything dies and you just get a new one or whatever. Then there's this connector for a separate daughter board that just has the 2 front panel idiot lights on it, and marked plus 5 volts green and red. That just means that the LED anodes are connected to 5 volts, and the cathodes are sunk through the microcontroller, presumably through resistors. That's a fairly common technique. Then there's a ceramic resonator for the microcontroller. Programming header has 5 volt supply. That's obviously because when this thing is programmed, this whole board isn't going to be powered up. Mode, that's probably some kind of setting thing for just telling the microcontroller, or just setting the microcontroller into programming mode. Transmit receive, with the transmit and the ground having some kind of a snipped off component leads, which might be some part of the programming process or something. CNVSS, don't know what that is. Ground and reset. Then on the underside of the board is that, and then there's just a little warning buzzer over there with a snubber dial, because this is one of the electromagnetic types where there's a little coil that you PWM at a couple thousand cycles per second, whatever the resonant frequency is, and that just moves the diaphragm. Then on the other underside of the board, there's a microcontroller. Don't know what it is. It's marked 0C014 A2H1. That could easily be an in-house part number, but it's almost certainly going to be a microcontroller of some sort. There's an LM324 made by Texas Instruments, which is somewhat interesting to see, as the P117 and P118 both had some obscure Chinese versions of an LM324 marked to AS324, but they're probably effectively the same chip, although maybe the parameters are a bit different. But whatever. bunch of resistors and capacitors. That's the battery relative negative terminal, and that goes to a pair of current sensing resistors there. That, which is almost certainly going to be the Kelvin connection right there for those sense resistors. And the other Kelvin connection is probably drawn somewhere on this trace, which probably is very little current and it's fairly thick. So probably some combination of those means that there's very little potential difference across that trace. That could also be why it's so thick, is just reduce that so that they can take their Kelvin connection off of it somewhere over here, what's probably easier to do on this particular layout. Then there's this FET, which is just controlling the current flow, or the current into the or the charge current into the cell, or into the battery. And it's probably going to be P-channel, judging by the fact that it's serving as a high side switch in this application. That's probably just a current limiting resistor. Or I think it might also be a really big fusible resistor, and it's using that in application. One interesting thing is that this uses as the element in the overcurrent protection fuse is just a bit of a trace on the PCB instead of a discrete fuse. Don't know why they did that, because that can be a bit harder to design as far as getting things right, but given the fact that it's only 20 volts or so at fairly low currents, probably things like braking and clearance and arc quenching aren't a really big deal. Although both of the other ones implemented that as a discrete, as a discrete fuse instead of using something on the PCB. These are all the underside connections on the transformer. Those two which go. This is the master neutral bus for the thing. Although the transformer is also connected to the the 12 volt hot. So what they're probably doing is that the actively switched winding in the transformer, that's just being used as a single-ended one switching device type switch mode supply, which is fairly common in these small ones. And then what they're doing is the load output is being drawn off of the 12 volt hot, so that means that they only need to increase the potential by say like 8 or 10 volts in the transformer, which makes reasonable sense. And it's just a bunch of screws holding down the various heat sinks. And there's a bit of flux gunge around that FET, which means that probably heatsink assembly, because I don't see any kind of a solder mark on these, and there's also solder, or no, there's not on the, or yeah, there is on the high current thing. Is that probably the heat sinks and the FET there, and the Schottky rectifier there were probably installed after the fact, but this whole board was full soldered, which you can tell by those little bits of adhesive goo under pretty much all the switching, all the various devices that I can see on the side of the board, which also looks to be a fairly common soldering technique that these chargers employ. But yeah, it's a thing.